Hello everyone. In the previous video I made, I discussed a molecular mechanism by which THC alters neuronal activity. Today I'm going to be talking about how this mechanism can alter stress. Stress is the most common reason people report for the use of marijuana. Indeed, it has been shown in various animal models that marijuana can alter stress. However, these effects vary depending on dose and usage frequency. For example, low doses are shown to reduce stress, while high doses can have the opposite effect and actually promote stress. In addition, first-time users often experience an increase in stress, while experienced users become tolerant to this. THC is the primary psychoactive ingredient in marijuana that activates cannabinoid receptors. In my prior video discussing the molecular mechanism of THC, I explained that the primary effect of cannabinoid receptor activation is inhibition of neurotransmitter release. This mechanism ultimately reduces neuronal signaling in various parts of the brain. But how does this mechanism explain its effects on stress? In this video, I'll describe how the brain controls stress and how THC alters this process. I'll first begin by describing how your body normally controls stress. The primary areas in your brain that control stress is the hypothalamus and pituitary gland. The hypothalamus receives information from various brain areas to determine whether to initiate the stress cascade. Meanwhile, the pituitary gland is able to release hormones into the blood that carry stress signals to the rest of the body. The stress pathway in your brain starts in the hypothalamus. The hypothalamus releases a hormone called corticotropic releasing hormone. Corticotropic releasing hormone then travels a short distance to the pituitary gland. When the pituitary gland senses corticotropic releasing hormone, it begins to secrete adrenal corticotropic hormone into the blood. Adrenal corticotropic hormone then travels to the adrenal glands located just above the kidneys. The adrenal glands then release stress hormones such as adrenaline and cortisol. These stress hormones can signal the rest of your body to prepare for threats. For example, hormones increase your heart rate, which increases delivery of oxygen-rich blood to your muscles. They also inhibit your digestive and immune system to conserve energy for immediate threats. In the short term, this can be helpful, as it allows you to respond rapidly when you are in danger. But in the long term, this can be detrimental, and you can develop heart problems, digestive issues, and susceptibility to infection. As a result, many people try to find ways to reduce chronic stress. So how does THC affect this? As I just mentioned, the stress pathway is mediated by a signal that travels from the hypothalamus to the pituitary and then the adrenal glands. This pathway is called the hypothalamic pituitary adrenal axis. The hypothalamus receives inputs from brain areas that process emotional state, such as the amygdala, hippocampus, and prefrontal cortex, to determine whether to initiate the stress cascade. The CB1 receptor is present at several parts of this cascade, and as I mentioned in my previous video, activation of the CB1 receptor will inhibit neuronal signaling. At the level of the hypothalamus, cannabinoid receptors are expressed on excitatory glutamatergic terminals projecting to CRH-producing neurons. Binding of THC to these cannabinoid receptors inhibits the excitatory signals going to CRH neurons. This results in reduced initiation of the stress pathway, and thereby reduces stress. At the level of the pituitary gland, cannabinoid receptors are expressed on ACTH neurons. Binding of THC to CB1 prevents ACTH release, and as a result, propagation of the stress pathway is further reduced. At the level of the adrenal glands, cells that make stress hormones such as adrenaline and cortisol also contain cannabinoid receptors. Binding of THC to these receptors reduces release of these stress hormones. So as you can see, THC interacts at nearly every part of the stress pathway, and these interactions reduce stress. Therefore, THC can inhibit stress at many levels of the HPA axis. If THC acts to reduce stress at so many parts of the stress pathway, then why does dose matter? Most of THC's stress-relieving effects are present at low doses, but high doses often produce the opposite effect. As I have just described, the activation of the hypothalamic pituitary adrenal axis promotes stress. Initiation of this pathway is determined by the amount of excitatory input coming from brain areas such as the amygdala, hippocampus, and prefrontal cortex. Whether these brain areas send a signal to the hypothalamus depends on a balance of neurotransmitter signaling. The neurotransmitter glutamate provides excitatory drive in these areas. The neurotransmitter norepinephrine and serotonin also contribute to this excitatory drive. Meanwhile, the neurotransmitter GABA provides inhibitory input that can reduce the activity in the amygdala, hippocampus, and prefrontal cortex, as well as areas that release norepinephrine and serotonin. For some reason, low doses of THC primarily inhibit glutamate inputs to the amygdala, hippocampus, and prefrontal cortex. This results in a reduction of excitatory inputs, and the balance of activity shifts in these brain areas towards inhibition. This inhibition prevents initiation of the hypothalamic pituitary adrenal axis and thereby reduces stress. However, at high doses, the neuronal signaling at inhibitory GABA terminals are also blocked by THC. This results in reduced inhibitory input to the amygdala, hippocampus, and prefrontal cortex. In addition, the reduced inhibitory input into the norepinephrine and serotonin system results in an increase in signaling from these areas. This shifts the balance towards excitation, which then promotes activation of the hypothalamic pituitary adrenal axis, and thereby enhancing stress. Stress is mediated by the hypothalamic pituitary adrenal axis, also called the HPA axis. Cannabinoids can inhibit many parts of the HPA axis. This includes excitatory inputs to the HPA axis, pituitary propagation of the HPA axis, as well as adrenal release of stress hormones. Low doses reduce excitatory drive on the HPA axis, while high doses increase excitatory drive on the HPA axis. I find these dose-dependent effects quite interesting, and it should inform future studies aimed at using marijuana therapeutically. Thank you for watching. Sources to all the things I discussed in this video can be found in the description below.